Hello, thank you for coming back for this hopefully moderate in length video to help finish some of the problems that I did not get done in class today. I'm going to be working in your class packet. I will remind you what we did on page 5 that leads into what I'm going to be showing you and calculating on page 6 and 7. So let me go to my smart notebook. Here, today's calculations are going to have two ways of doing enthalpy calculations. On the first page, page 5, I'm going to know the enthalpy of these two chemicals as they dissolve in water. And I'll be able to use that known enthalpy value for the heat of solution to calculate the temperature change. Then on pages 6 and 7, I'm going to do the opposite. I'm going to know the temperature change because I'm collecting it in a lab-like experience. And from that temperature change of watching a chemical dissolve in water, I'm going to be able to calculate the enthalpy of the solution. These are two enthalpies that we will not have been given in our resources, but we'll calculate them from lab data. So on page 5, I will upload a PDF of my solution to how we calculate this temperature change from the known enthalpy. I will also upload the PDF that I did in class for this solution of how to do the same calculation with ammonium nitrate. But my primary concern here is to work with you on this activity. I'm going to take KCl and I'm going to dissolve it in water with vernier probeware doing the temperature measurement. So I have 100 mils of water. I'm going to pour it into a styrofoam cup that's just balanced here in a beaker. I have a stirring bar in this beaker and I'm going to put it on a stir plate. Now this temperature probe is going to record the temperature. I haven't started the software yet, but I'm going to put the temperature probe in the water solution so that we can get a base temperature. Here is the mass of the potassium chloride. You see that it is a simple white crystalline solid that looks a lot like table sugar. All right. Here I have the software for vernier, the temperature probe. I have the temperature probe in the solution. I'm going to start collecting data. And you can see that the initial temperature is right around 24. 24, 23.9, it goes back and forth every half a second. Here I have the graph showing the initial temperature of the water alone before I've added any salt. It's important that you get this baseline so you know your TI. I will come back and record that on our data table in just a minute. Now I'm taking the salt and I'm going to add the salt to the solution. This is KCl. You can see what's happening as that salt dissolves is that the temperature dropped. And once the temperature drops a maximum amount, it levels off and it will eventually start to slowly go back up. Because if I were to leave this coffee cup in the room for 3 hours, that water would come back up to room temperature. So the beaker of water, even in a styrofoam cup, won't stay at this colder temperature. So you can start to see the gradual incline. What I'm interested in here is the initial temperature of the water before the salt was added, the KCl, and this lowest temperature. So I am going to stop the data collection, and I will come back and talk to you about these two numbers. One of the numbers is right here up on the top. At 0 or 0.5 seconds, we're going to call this 24.0 for our initial temperature. Then let's look to see what the temperature is right here. What is our lowest temperature? I see 18.456. I'm looking through my temperatures. It looks like my lowest temperature is right here at 18.2. So I am going to record those two temperatures, 18.2 as my T final and 24.0 as my T initial. All right, so I've got the data collected and I will show you my calculations. Here I have completed my data table. I've shown you here that the initial and the final temperature of the water have been added. And here I've got the calculation. How much energy was involved in the reaction? Here I have to do my Q of the reaction is negative Q of the water. You solve for energy with the Q equation. This is what you must write to get the sign correct. So Q of the reaction equals negative Q of the water. Substitute in MC delta T. Put in the data that we collected, including this side calculation of your delta T. You end up with a positive amount of energy that this dissolving process of KCl required. So that's a little bit of energy that was required because you only dissolved a little bit of KCl. Well, how many moles of KCl did you dissolve? How many moles? Take the mass of the KCl that we actually measured out and added to the water. Use the molar mass of KCl to convert that little bit of KCl to the mole quantity of KCl. Now we have this relationship. This little bit of KCl required this little bit of energy. We've got to turn that into a molar enthalpy, and a molar enthalpy is how many joules or kilojoules per mole. A molar enthalpy is kilojoules per mole. So here's the little bit of energy that was given off by a little quantity in moles of KCl, convert joules to kilojoules, and here's my end result. That process in kilojoules per mole is 19. And that is literally kilojoules per mole. All right, so the experimental thermochemical equation is KCl as a solid going to be KCl as aqueous. I put the 19 kilojoules on this side because it is endothermic. The reaction is for 1 mole. This quantity of 19 is for 1 mole. I put it right in. So now I'll go on to the second activity on page 7, where I'm going to take another 100 mils. Nope, excuse me. This is 99.0 mils of water. 99.0 mils of water, and combine it with a mass of KOH. KOH is a little lumpy, a little more than granular, a little clunky. So first I'm going to take my water with a stirrer, put in my probe, and get a baseline. Let me show you where I'm at. in our class notes on page 7, I am here on this document. I'm going to show you that I have filled in some of the data already. 99 mils of water. I have already massed out 9.15 grams of KOH, a different chemical. So I will stop sharing that and I will go to my software now and show you the beauty of using computer probeware. All right, let's start this data collection. Here, my initial temperature is 23.8. 23.8, I've got the flat line, and I just want to make sure that line stays right there. I've got a good initial temperature. Now I'll take my potassium hydroxide and I will add it to the beaker. Here you see the temperature rising. It looks like it has risen all that it will. The temperature has peaked. And now it looks like it will slowly go back down. Eventually, if I sat here for an hour and a half, to room temperature. So I will it's a little unusual, but I'm going to go with it. I am going to stop sharing that and come and do the calculation for you. Well, first I'll show you, excuse me. First, I'll show you that we're going to use 26.0 for our minimum, our initial temperature, and we're going to use, what is our highest? 26, 26, 26. Excuse me. Right here is our highest. 26.3 is our highest. Right here would be 26.3. So I have the temperature data in our data table, and now we'll finish up our calculation. For the KOH, we've got an initial temperature and a final temperature that was higher. I described the qualitative data here. Calculate the delta T, T final minus T initial. Make sure you recognize that whatever the water is doing is the opposite of what this reaction of dissolving KOH will do. So the Q of the reaction is negative Q of the water, which is M of the water, specific heat of the water, delta T of the water. Put in your numbers, and I have this interesting number of a negative 1,000 joules with 2 sig figs. Negative 1,000 joules is the answer of the Q of the reaction. That is a little bit of heat for just a little bit of KOH that was dissolved in water. How much KOH? Turn that little bit of KOH into moles by using the molar mass. Now I can use those two quantities, the little bit of heat generated by the little bit of KOH, and convert that to kilojoules to get The experimental value of negative 6.1 kilojoules per mole. The tricky part is when you put that into the thermochemical equation, and this is the experimental thermochemical equation. When the solid KOH dissolves in water, it gives off 6.1 kilojoules for every 1 mole of KOH, but it's a product in the thermochemical equation, so I put it plus 6.1 as a product. I have demonstrated those 2 activities in your class notes. Tomorrow we will start class with practicing another one. You'll have one in your homework also. I wish you all the best in your calorimetry. This is the hardest. It gets better. Best to you.